In this video, we are going to be covering ANOVA, which stands for Analysis of Variance. ANOVA is conceptually similar to an independent t-test, the one that we are covering today. We use it when we have two groups or conditions where each person relies in only one condition, such as like male and female, but in this case we can think of something like ethnicity. One of the issues that we have is that we have more than two groups. How do you compare means? You can't do mean 1 minus mean 2 minus mean 3. That's just not going to work very well. Because which mean comes first, which means comes second, it doesn't work very well. So instead we look at how much the scores vary from each other. Hence, analysis of variance. We're going to look and parcel out all the different types of variances that we can and are available to us. We're going to do this by using what's called an ANOVA table. You can think of it similar to a Sudoku table in some regards, in that once you have one piece of information, you can slowly fill out the rest. There will be an in-depth calculations video separate from this one. This video will only give a cursory, quick view of it. Once we have done an ANOVA table, we run a Tukey's post hoc. The only time we run a Tukey's post hoc is going to be if we find significance. We will go more into what the post hoc analysis is a little bit. In addition, just like before, we are going to calculate effect sizes. Again, we only calculate an effect size if there is significance. If there's no significance, then there is no need to calculate an effect size because the treatment has no effect, and if something doesn't exist, it has no size. We'll talk about SPSS and APA style. So back to my point, comparing the means. On the bottom, you can see we have mean for rote rehearsal, the mean for imagery, and the mean for story. But you can't compare those to each other because all of a sudden if you do 4 minus 5.5 minus 8, that's different than if you do 8 minus 5.5 minus 4 or 5.833. It doesn't make conceptual sense to do it because there's no first, second, or third. It's all arbitrary because the groups have no meaningful order because they're nominal data. That begs the question, or brings to mind, why not just do multiple t-tests? Well, the issue is that we are going to raise our type 1 error, our family-wise error, because every time you conduct a test, you have a 0.05 chance of doing it. So in our case, you'll have 1 minus 1.05, which would give you 1 minus 0.86, which gives you 14% chance of creating a type 1 error or finding one. Then you can instead be like, well, what if we just lower the alpha rate? You can use the Bonferroni adjustment. You can divide whatever you set your alpha to initially by the number of comparisons. However, when you take a look at this, with just 3, we reduce it to 0.017, and that's a pretty drastic change. That's a 66% reduction, making it much harder. And why should we make it harder to reject something when all we need to do is run an ANOVA instead? Specifically because the ANOVA keeps the type 1 error at 0.05 without raising the type 2 error. Now that we know that it makes more sense to run an ANOVA, let's talk about the different types of variance. First is the total variance, which is all of the variability of all the scores from the grand mean, which we talked about in a previous slide. We have between group variance, so how much each group is different from the others, how far away apart they are, and within group variance. It is important to realize that group design and group variance are different things. Group design tells you what type of analysis should be run. Group variance tells you where the variance is coming from. Total variance, again, measures how much all the scores individually differ from the mean. So it's all the individual scores compared to the mean. Measures of within group variance are how much each participant's score differs from the mean for their group. So within is within a group. So as in one group, that's the variance we're looking at. And how much those scores. This is always going to be considered something called error, because everybody is going to be given the same treatment in that one group. So therefore, ideally, if it was only up to that treatment, and the only thing that influenced that score is the treatment, everybody would score the same. But due to the fact that we are all unique and individuals, we all have different personalities, temperament, physical, mental capabilities, we end up with different scores. Between group variance, this is what we are looking at and what we consider the most important, essentially. This is due to the fact that between group variance shows us how much each treatment differs from each other, so how much of an effect they have, essentially. The greater the between group variance, the more they are distant from each other, the groups, the greater the impact the treatments have on the outcome. Let's take a look at things that contribute to variance. So we have the independent variable effect, and then we have error, or everything else. In a between subjects ANOVA, the reason this is the case is because all we are able to know about is the independent variable effect. That's the only thing we have any type of statistical control for. We know who is in what group. That is it. That's all we know for this particular test. Therefore, anything else that influences the score is called error, because it's something that we are unable to account for. Now, there are tests later on and more advanced tests that can account for more things, but in a simple between subjects ANOVA, it is just going to be the independent variable effects and error. Now, what influences between group variance is going to be the independent variable effect plus error. Now, you might be thinking, well, independent variable effect, okay, that makes sense because everyone's their own group, but why is error there? Well, error is present everywhere. We can't always control for it, and sometimes maybe one group is treated a little different, or one group of people have a bad day and another one has a really good day. We don't know exactly. Due to that, we assume that there is some error in there. We're not able to measure it or know exactly what it is, but in this particular analysis, but there is error. And then, as talked about before, within group variance is all error, because if everybody got the same outcome, if everybody, for instance, got the same water for their plants in each group, and we had, let's say, different types of alkalines or what have you, that type of water, if they all get it, should cause the plants to all grow exactly the same. However, that's not going to be the case due to different genetics. It could also be something similar to different families. Within families, the kids turn out differently, though everybody has the same parents in that family. So any differences in, say, height, personality, intelligence, anything you can think about within a family, there's going to be error. Any variation, that would be considered error because it's within a group. A family is a group. Next we have what's called the F ratio. That's this F right here, where it's the F equals the between group variance over within group variance, which can also be thought of as the independent variable effect plus error over error. And so what happens is, if we have no independent variable effect, this right here becomes 0. And let's just state that you can write this down, error equals 5. So 0 plus 5 becomes 5. 5 over 5 equals 1. Hence, if the independent variable has no effect, it equals 1. And our F is going to become just like our F obtained. Anytime we run an analysis, we usually have an obtained value. In this case, it's going to be called F obtained. So in order to determine if something is significantly greater, we're going to have a critical value. For every obtained, we have a critical. Here too, we have F obtained, and we're going to have F critical. And we have to see if it's significantly greater than 1. But to see if it's significantly greater than 1, we need to see if our F is greater than 1. I have to see specifically if it is greater in regards to the critical value. So it needs to be greater than the critical value, just like we have in the past. ANOVAs are only two-tailed. And here we have two types of hypotheses, essentially. We have our null and our alternative. In our null, all groups are equal. However, we are not going to state that not all or all are not equal. We will say not all mu's are equal. Because all we need is one not to be equal in order to negate the null hypothesis. And that's the point. We just need to negate it. We don't need to completely reject it. We just need to say one part of this isn't true, and therefore we will find support for alternative if that were to be the case. So we can find something like mean 1 equals mean 2, but mean 1 doesn't equal mean 3. Since mean 1 doesn't equal mean 3, we know that the null isn't true because they're not all equal. For it to be all equal, mean 1 would have to equal mean 3.